Alright, hello chemistry class. Today we're going to talk about types of energy and the laws of conservation of mass and energy. So to start off, let's talk a little bit about the forms of energy. There's two main ones that I'd like you to know. Kinetic energy, which is energy in motion, so a bike rolling down a hill, or a person running, or the motion of the molecules in a solid or a liquid or gas. All those are kinetic energy. The general form is kinetic energy is equal to 1/2 of the mass of the object times its velocity squared. You don't usually use that too often in chemistry, but it's a good reminder. The average kinetic energy is also a measure of the temperature. So when we're measuring the average kinetic energy of the molecules in, or the particles in a substance, that's the temperature. So if those molecules are moving fast, really fast, they're probably in a gas state at a high temperature. They're kind of moving a little bit slower, kind of flowing over each other. It's a liquid at a lower temperature. And even lower than that, you've got solid particles which are kind of vibrating in place. That's kind of an interesting thing to keep track of. The average kinetic energy is also equal to temperature. Next, we're going to talk about potential energy. So potential energy is any type of stored energy. You're probably familiar with gravitational potential energy from physical science, which is mass times gravity times height. I didn't include that here because you don't need to know it really. There's also electrical stored energy, like a battery, and chemical stored energy, which is kind of probably what we're going to focus on since we're in chemistry. So it's no secret that if you burn gasoline, you get quite a bit of energy from it. So the arrangement of the molecules and how they're put together gives us that stored energy. Next, let's talk about how we measure energy. The SI unit that you'll use most often is the joule. So you can have a kilojoule, a microjoule. All those metric prefixes work with joule just the same as they did with meters and grams and everything else. The original unit for energy, one of the original units anyway, was a calorie. And they defined a calorie as the amount of energy it took to raise the temperature of 1 gram of water 1 degree Celsius. Interesting thing, 1 calorie with a capital C is 1,000 calories. So if you look at a food package, you're like, oh, it's only got like 500 calories. If it's a big C or a little c, it actually makes a pretty big difference. Most of the food labels you'll see, they actually use the big C. Tricky food companies. And just as a unit of conversion, 1 calorie, little c, is equal to 4.184 joules of energy. Joules is abbreviated with a big J like that. 1 big C calorie would of course be then equal to 4,184 joules. So there's a big difference there. Alright, now the law of conservation of energy. So we used to think that energy cannot be created or destroyed, just transformed from one form to another. So you could go from potential to kinetic, kinetic to potential, lots of different things, electrical to mechanical, lots, you get the idea. But then this weird guy liked to stick out his tongue a lot, at least in one picture. Einstein came along and he changed that. We'll talk a little bit more about that here in just a second. But let's talk about the law of conservation of mass. So it's basically the same thing. Mass cannot be created or destroyed, just transformed from one form to another. That's what a chemical reaction is doing. It's transforming the mass into something new. So under normal circumstances, that works. Again, Einstein kind of threw a wrench in our laws. That's okay. The important thing is that this means the amount of atoms that go into a chemical reaction need to be the exact same as the amount of atoms that come out of that reaction. Balancing chemical reactions is a big part of that. You've got to have the same number of atoms of everything on both sides. So Einstein's contribution, I told you we'd talk about this. His famous equation, E is equal to mc squared. It's on a lot of t-shirts and posters and such. It means energy is equal to mass times the speed of light squared. So we know, at least in theory, that the speed of light is really, really fast. So if you times anything by the speed of light squared, you get a really big number. So a little bit of mass can turn into a whole lot of energy. So this means that mass and energy are actually interchangeable. You can turn energy into mass and mass into energy. Only under extreme conditions. Those extreme conditions most often are going to be fusion and fission. So fusion is what's happening in the sun right now, keeping us nice and warm, at least if the clouds clear out. So fusion is combining atoms, and in our sun, they're combining hydrogen atoms into helium atoms. And when that happens, they lose a little tiny bit of mass. That little tiny bit of mass times the speed of light squared equals a whole lot of energy. The sun's pretty darn hot, if you haven't figured that out by now. Fission is the exact opposite. Fission is the splitting of atoms. So this is what's going on in nuclear bombs. What they actually do is get fissile material like uranium-238, bombard it with a neutron. That neutron breaks up the atom. You lose a little tiny bit of mass, and again, that little tiny bit of mass times the speed of light squared equals a big boom. We've seen pictures, of course, of the devastation of Japan, Nagasaki, and Hiroshima, and nuclear test site footage. It's a big release of energy. So that's pretty much the laws of conservation of mass and energy and the different forms of energy. Hopefully now you can work on the 2-1 practice problems and you should be good to go. See you on Monday.